Right, good morning, everyone.
Morning, sir.
How are you?
Morning, sir.
Right. Last time, I think we looked at the revision for the consolidation activity that I gave you. Then we had started on this activity here in electrostatics, where we had to revise some of the exercise that we did here. Right. So I'm just gonna continue from here. I gave you some activity on electrostatics. I think you're still busy with that one. Are you done?
Which one, sir?
Electrostatics. I think I gave you an activity consolidation. Was it exercise? Uh, is an activity that I gave you. This one here.
Exercise. I think
Consolidation.
exercise.
Exercise 14.
Yeah, exercise 14.
Huh?
Yeah, exercise 14.
Yeah. Yeah, it's 14. Yeah.
Mm.
I'm not sure what date I put today for you guys to finish. I think it was today or tomorrow. I'm not sure.
Oh, yeah. Yeah,
Yeah.
today.
Come again.
Yeah, you gave us Monday for
I
today.
gave you Monday. No? Okay. All
Yeah.
right. So what I'm gonna do, I'm just gonna give you others who are still busy sometime. Then Friday we're gonna go over this one. Clear?
Okay.
All right. Friday we'll go over this consolidation activity that I gave you. I think Monday, right? Then Friday we'll go over it, just to give people who haven't done it chance to go over it. All right. So I'm just gonna finish up. This exercise on electrostatics that I gave you last time. We're looking at question number 2, where we're looking at the spraying gun, and we said some of the advantages there. It will stick to the object, all right? Less paint is wasted, all right? You don't have to move the nozzle around the object as you would have to. And we also saw that the paint sprays easily on the surface. So those are some of the advantages that could have listed. Right? There could be
Yeah.
more depending if it's relevant. Right, then we move on to question number 3. It says lightning conductors are used to protect homes from being struck by lightning. Briefly explain how a lightning conductor works. All right, we know lightning uh, in the clouds, we're going to have a buildup of charges, positive and negative. All right, we've got maybe positive on the top of the cloud, negative on the bottom of the cloud. You did that in grade 9, I guess. Right, then
Mm.
solution. A lightning conductor is a tall metallic spike which has its base buried in the ground, and um, its spike is a few meters taller than the house. So, as in this example here, that one becomes your lightning protector there. So it's a bit higher. It has to be taller than the trees around it so that the charge touches that one first, right? So when lightning strikes, it moves through the air, taking the path of least resistance. The basis of the clouds becomes negatively charged. So it means on the cloud at the bottom it's negatively charged, at the top it's positively charged. So the electrons in the lightning conductor are repelled down into the earth, right? The spike becomes positively charged. Lightning will therefore follow a path through the earth and down to the conductor safely, taking extra electrons deep into the earth. So basically, all the charges that are coming from the lightning, they're gonna strike here, then they are sent to the ground. So harm is averted from whoever could be on that particular way. So the lightning conductor will transfer all the extra charges into the air. Right.
Mm.
Actually, lightning
Yes.
travels both ways, up to the sky, down to the earth during a storm. The positive charged ions in the air moves. So depending with where the net charge is, so there will be transfer of electrons either way. So it's not specifically in one particular direction. All right. So that's what we have there. On the lightning conductor. All right. Then the next question says two positively charged spheres are brought up to touch each other. The charge on sphere A is 20 nanocoulombs, where sphere B is positive 6 nanocoulombs. Right, state the law of conservation of charge. So this law, you have to memorize this one. So it says the total charge in an isolated system remains constant. The total charge in an isolated system remains constant. So it's nice and short, so it's easy to memorize this one. 4.2, calculate the charge on each sphere when they are separated from each other. So basically what is going to happen here, the two charges, they're going to attract, all right? They're going to
Yeah.
attract. When they attract, then they're going to share charges, all right?
Yes.
When they share charges, then when they have the same charge, then they repel one another. Just like we know, like charges repel and like charges attract. But in this particular case here, this could be not a right example, because you see all of them are positive. So someone might argue to say this one, they are both positive, so they are repelling already. But check here, there's one that will have more electrons than the other one. So a good example would be a plus and minus, so that we have unlike charges attracting, sharing electrons, then they have the same charge, then they repel. So this one not exactly a good example because of the plus and the plus,
Yeah.
right? Okay, right. Then what are you gonna do? You're gonna, for you to get the final charge after they've shared the electrons, you have to add the two, Q1 plus Q2, divide by 2. So the charge on the first sphere is 20 nanocoulombs plus the 6. So it becomes 26. Then you divide the 26 by 2. Then you get your 13 nanocoulombs. So as you can see, the 20 went down to 13 and the 6 went up to the 13 there. Right. So they now have the same charge. Each one now is 13 nanocoulombs. Now they've got the same charge, same protons, number of protons, same number of, then they repel, right? So that's
So,
the net charge. Yes.
so I have a question. So, like you see, like when they say, like if they have to say two metal spheres are brought to each other and then they are separated again, what
Yeah.
formula can we best use to like solve like the electrons of one of the spheres that was brought away?
Okay. Come again. What's your question?
So I said, for example, sir,
Yeah.
let's say they give us a question with two metal spheres.
Yes.
They have a charge when they are separated, and then when they are brought toward each other, and
Yeah.
then they are brought toward each other and then separated. And
Yeah.
then we must like calculate the number of electrons, the new number of electrons.
Okay. The question normally comes in two different ways. They would ask you how many electrons are on the sphere, and they would also ask you how many electrons are transferred. Right. So basically, if it is to do with calculating the number of electrons on the sphere, so you simply use that
Yeah.
Q is equal to N number of electrons multiplied by QE, where QE is the charge on an electron. So you're gonna take the charge. In this example, let's say you want the number of electrons on the maybe the 20 nanocoulomb object. So you're going to take the 20, that becomes your Q, is equal to
Yeah.
N. You're looking for number of electrons. Then you're going to multiply it by the Q, which is the charge on an electron. Then you make your N the subject. Then you get how many
Oh,
electrons you have.
okay.
Yeah. Right, but now
Okay.
the question, there could be a twist, because normally they ask you how many charges were transferred. So basically,
Yeah.
if
Yeah.
in this example, for example, here, initially we had 20. Now the new charge is
Yeah.
now 13 here. So if you want to know how many electrons were transferred, you're going to have to
Use that
subtract
for
the final charge minus the initial charge. So you're going to subtract 18 nanocoulombs minus 20 nanocoulombs. Then you divide, that becomes your Q, because you want how many electrons were transferred. Then you're going to substitute the Q in the formula. Q is equal to NQE. Then you get your number of electrons.
Okay.
Yes. So basically what is happening here, there's one object that is giving electrons, then there's one that is gaining. Which one gives electrons is the one that is more negative. So like I said,
Negative.
you put these two numbers on the number line. So 6
If
is
transpose
closer
0.
to the negative numbers. So the 6 is,
Yeah.
yeah, is more negative. So the 6 is going
Yeah.
to give electrons to the 20. That's why you see the 6 is becoming more positive. It's becoming more
Yeah.
positive. It's becoming a 13. And the 20, it was way far from the negative. Now it's getting closer to the negative because now it's becoming a 13 here.
Okay.
Yes. So the
Yeah.
questions are of two types. You want number of
Mm.
electrons on the sphere, or you want number of electrons that were transferred. If it was transferred, you have to do a subtraction, final charge minus initial charge. Then you divide by
But
the
sir,
charge on electron. Yes. Yes, Zinedine, is it network? I think you are cut off there. Yeah.
how is 20 nanocoulombs the final? How is 20 nanocoulombs the final charge?
You are breaking there. Can you ask again?
So I said how is nanocoulomb the final charge in this case?
Okay, you're saying how is nanocoulomb the final